Okay, let's have a look at proving the following. That the probability of the empty set is equal to 0. This is something that looks very obvious, and in mathematics it's usually these obvious things that are the hardest to prove. But there's a few ways of proving this, and I might do some videos on the other ways to prove this, but for this proof we're just going to look at the axioms that we'll need to be able to prove this. And the axioms that we need are the fact that A, unity with the null set, is A, and A's intersection with the null set gives us the null set. So these are two axioms. The first one just means that we take all the elements that are in the set A, as well as the elements that are in the null set or the empty set, which is nothing, and the result is just the set A, because we've not added anything in this unity, we've added no elements. In this set, well, in this axiom here, the set A, if we take the intersection with the empty set, it means that what elements are in A that are also in the empty set. And there are no elements in A that are also in the empty set, because the empty set has no elements in it by definition. So our result is again just the empty set. So to start this proof, we'll have to do the following. So the proof will start by saying let A be a non-empty set. Okay, so we start by stating that A is a non-empty set, because if we don't state this, then you do your proof and then you try to substitute the empty set into it, and it kind of falls apart. So we need to have a that isn't the empty set. And then from here we just use these two axioms to be able to prove our statement here. So we'll say that A is equal to A's unity with the empty set, and this is an axiom, so that's fine. Then we say that the probability of A is equal to the probability of A's union with the empty set. Okay, this is just taking the probability of both sides. From here, we have to rewrite this right-hand side here, and we can rewrite it as follows. We can say that it is equal to the probability of A plus the probability of the empty set. And we can do this because from these axioms we can see that A and the empty set are mutually exclusive, right? So if two sets are mutually exclusive, it means that if you take the probability of their union, it is equal to the sum of the probability of the two sets, because when two sets are mutually exclusive, it means they have no elements that are in common. So taking the probability of their union means taking the probability of what's going on here plus the probability of what's happening on this side. And that's exactly what's happening. So knowing this, we can, so to say, take out this middle part here, and we can then say that the probability of A is equal to the probability of A plus the probability of the empty set. Okay? Because we can see this is also equal to that. Then we subtract the probability of A on both sides. So we'll just say that the probability of A minus the probability of A is equal to the probability of the empty set. And here it is very obviously to see that the probability of the empty set is indeed 0. And this is the proof by using these two axioms and the fact that the empty set is mutually exclusive with any other set, that we can use this specific rule here, because this rule is, so to say, the core of this proof, that they are mutually exclusive and that we can write the unity in this form. And then you can just subtract the probability of A. And this is also a very important thing. This is why we put this at the beginning, to show that A is a non-empty set. Because if A could be an empty set, you'd have the empty set here. You'd have the empty set here. And you'd have that the probability of the empty set is equal to the probability of the empty set plus the probability of the empty set. And now you subtract that from the other side, and you show that the probability of the empty set is 0. So you can do that. I mean, you could say that the probability of the empty set, if A was to be a set that is empty, would be equal to this, right, which would now again be the probability of the empty set, or the A set that we now discussed, plus the probability of the empty set. But then you have to show that the empty set is mutually exclusive with itself, which is a bit weird to do, because the union gives the empty set and the intersection gives the empty set. So it's just a bit easier mathematically to take a set that isn't empty and do the proof. But at the end of the day, you'll be able to do the proof either which way. It's just easier to have a set that is non-empty.